Thanks for the introduction, and I'd like to first thank the organizers for putting together this wonderful workshop conference and for giving me the opportunity to speak. So let me see. Okay, so I'm going to talk about some interplay between non-invertible global symmetries and entanglement entropy. So the talk will be based on these two papers, mostly the second one, in collaboration with Brandon Rayon and Yunchin Zheng, and both of them are in the audience. Okay, so what's the setup? So throughout the talk, I'll be discussing 1+1D continuum conformal field theories. So famously, if you put the theory on an infinite line, so space is infinite line and time goes vertically, if you compute the entanglement entropy for the ground state of the CFT for this finite interval A, then the entanglement entropy has a leading universal logarithmic divergence where the coefficient is determined by the central charge C of the theory. However, so this entanglement entropy is defined by the von Neumann entropy for the reduced dense matrix rho A for the interval. However, the reduced dense matrix and the continuum CFT, to be very precise, is not really well defined. So the reason is because the Hilbert space of the theory on the infinite line doesn't really factorize as the Hilbert space on the interval and then the rest. And perhaps relatedly, the entanglement entropy naively diverges and requires some regularization. And there are different ways to go about these issues. And for today's talk, we are going to follow the approach suggested by Omori and Tachikawa a little more than 10 years ago. Well, the idea is to impose an explicit conformal boundary condition at the entangling surfaces. And because this is going to be important later in the talk, I'm going to spend a few minutes reviewing their proposal. So the idea is the following. So you first start with the theory on an infinite line, and then consider following quote-unquote topology changing Euclidean path integral. So initial time slice is this infinite line, and my final time slice is on the top, where this interval A of interest of length L sort of explicitly disconnected from the rest of the space. And to do so, what I do is you cut out these small semicircles of size epsilon, two semicircles, and you explicitly impose conformal boundary conditions B1 and B2 on these semicircles. Now, the result of this Euclidean path integral is some linear map between two Hilbert spaces, where you start from the Hilbert space H on the infinite line, and you map to this explicitly factorized Hilbert space. The Hilbert space is factorized now because the space is disconnected. I'm going to call this map iota. Now, to define the reduced dense matrix for the single interval for the vacuum state, which lives in this unfactorized Hilbert space H, which I denote as omega, what we do is the following. You first hit this map iota defined by this Euclidean path integral on omega. Now, iota times omega will now live on this factorized Hilbert space, again from the density matrix, and trace out anything that's outside of the interval A. In terms of Euclidean path integral, such a reduced dense matrix will be repelled by this kind of picture. So I'm doing a path integral on an infinite plane, where I have this small disk and also a small slit connecting the two disks excised from the plane. And on the disk, I impose boundary conditions B1 and B2. Now, by performing a conformal transformation, this geometry on the left-hand side can be mapped to a finite cylinder, where I still have this small, where my interval A now lives here. So in the picture right hand side, the base integral is nothing but it corresponds to the time evolution of the CFT defined on an interval. In other words, the reduced dense matrix rho A for our interval of the normalization is basically given by the exponential of the Hamiltonian along this interval direction. I'm going to refer to this interval Hamiltonian as open string Hamiltonian. Now, by using this explicit form of the reduced dense matrix, by applying some Hardy-like formula, you can compute the entanglement entropy in the limit where the size of the disk epsilon is much less than the length of the interval L. And you recover this well-known universal leading behavior. Now, there are some subleading terms. These subleading terms depend on the choice of conformal boundary conditions. For instance, at constant order, and so these two, you find these log G1 plus log G2. They don't depend on the length scale L. These GIs are so-called the G functions for conformal boundary conditions. And these log G1, G2 are also sometimes known as Updike-Ludwig boundary entropy. So the situation can be summarized like so. So there is some correspondence between the problem of entanglement entropies in CFTs and boundary conformal field theories. Once you choose explicit conformal boundary conditions B1 and B2 at the entangling surface. Under this correspondence, this sub-region Hilbert space H sub A corresponds to the open string Hilbert space, which I denote as H sub B1, B2. It's nothing but the interval Hilbert space of the CFT with B1, B2 imposed at two ends of the interval. The reduced dense matrix is nothing but the time evolution along the interval. In other words, it's the exponential of the open string Hamiltonian. The entanglement Hamiltonian, defined as the logarithm of the reduced dense matrix, is identified with the open string Hamiltonian. So far, so I have not discussed what determines these boundary conditions at the entangling surface. So if you are a continuum field theory person, then this choice of conformal boundary condition is totally up to you. If you choose different conformal boundary conditions, you will get different subleading behavior of the entanglement entropy, but the leading universal term doesn't change. However, that does not necessarily mean that choice of conformal boundary conditions are completely unphysical or uninteresting. Suppose you are interested in some macroscopic lattice realization of this conformal field theory. Say you have some lattice regularization where you have a well-defined tensor product Hilbert space. In such a case, there is many sort of numerical evidence that the entanglement spectrum that you get on the lattice for this critical lattice model agrees very well with the spectrum of the boundary conformal field theory, where you get some conformal boundary condition at the entangling surface. There was a paper a few weeks ago where they made an observation that in all the known examples where this numerical test has been performed, it seems like the conformal boundary condition that you get the entangling surface is the one with the highest G function. And I don't know why that should be the case, but it's sort of interesting observation. Okay, so for the rest of the talk, we'll try to understand what's the global symmetry structure of this entanglement spectrum. So the setup will be the following. Suppose your 1 plus only conformal field theory has a finite and potentially non-invertible global symmetry described by some fusion category. Now the questions we are going to be asking are the following. We want to understand how are these symmetries, fusion category symmetries, are realized by the entanglement spectrum. And we want to understand what are their imprints on the entanglement structure. More specifically, one may ask, how does the entanglement spectrum organize into different representations of the global symmetry? You can ask how frequently a given representation appears, does every representation appear, and so on and so forth. So for ordinary symmetries, many previous authors studied related questions using many different methods. And one nice diagnosis to answer this kind of question is to consider so-called symmetry resolved entanglement entropy. And I will come back to this later in the talk. So what is the goal now? So we are interested in the symmetries of the entanglement Hamiltonian, or due to this correspondence to boundary conformal field theory, we would like to understand the symmetry of the open string Hamiltonian. So picture will be like so. So I have my CFT defined on a finite interval with some conformal boundary conditions B1 and B2 imposed. And symmetry operators that commute with this open string Hamiltonian will in general be obtained by considering some topological line operator, D sub I, which is stretched across the interval. Now, when you consider such a topological line operator, you need to also specify what happens at the endpoints of this topological operator. In other words, you need to specify the junction operators y1 and y2 that sit at the end of this topological line di. And in general, this choice of junctions y1 and y2 is not going to be unique, but to define a symmetry operator, we want these junctions y1, y2 to be also topological junctions. So when you choose these junctions to be topological, this entire configuration defines an operator acting on this B1, H sub B1, B2 Hilbert space. So I denote as di y1, y2. And this operator is going to commute with the Virasoro symmetry. To be more precise, there might be a subtlety that in general, when you act by such an operator, these conformal boundary conditions B1, B2 may also change. And in general, this operator will map your HB1, B2 interval Hilbert space to some different interval Hilbert space HB3, B4. And since everything is topological, this operator sort of intertwines with the two Hamiltonians, or you can think of it as it commutes with the open string Hamiltonian and sort of defines the symmetry of the system. Now, consider a collection of these operators, di, y1, y2, for all different choices of I. So I labels my object in the fusion category, and y1, y2 labels all possible topological junctions. This collection of operators acts on this extended open string Hilbert space, where you take this H sub B, B prime, and sum over every B and B prime which are transformed into each other under the action of the fusion category symmetry. Now, this collection of operators, so if you take two of them, you can multiply the two by just putting the two operators next to each other and then parallelly fusing. This fusion coefficient, T, these are some complex numbers. It's in examples you can explicitly compute using so-called boundary 6J symbols. The details are not important, but so this collection of operators under this multiplication, they form an algebra. They define a symmetry algebra acting on the open string Hilbert space. And we're going to call this algebra a boundary tube algebra for the sake of this talk. In the literature, this was also referred to as strip algebra, because this is symmetry algebra acting on this theory on a strip. But in any case, the upshot is that this boundary tube algebra defines the symmetry algebra of your entanglement Hamiltonian. And I'm not going to get into details, but this same kind of algebra appeared in many different physical contexts. As far as I know, maybe this appeared first in this paper by KITP. This was more than 10 years ago. But there are many recent papers also finding this algebra in different physically interesting situations. Let me briefly give you a simple example. So consider two copies of the Eisenconformal field theory, the central charge 1. And the symmetry of interest will be G2 times G2 symmetry of the two CFTs, and the product of the two Kramers-Wannier symmetry lines. So N1 and 2 refer to the Kramers-Wannier duality lines of the individual Ising CFTs, and then we are when we consider the product of the two. So you have 5 topological lines here, and these 5 topological lines form a fusion subcategory of this symmetry of the Ising, double Ising CFT. And you can show that in this double Ising CFT, there exists a conformal boundary condition, B, which preserves, which is symmetric under this fusion category of these 5 topological lines. Now, in case you impose this symmetric boundary condition B at the entangling surface, you can sort of explicitly show that the symmetry algebra generated by these open string operators is something well known in mathematics. It was first discovered by Katz and Paljukhin. There's some 8-dimensional Hopf algebra. So the details are not important, but the fun fact is that historically this HA Hopf algebra is the first Hopf algebra that was discovered, which is neither commutative nor co-commutative. So it means that the representation category of this Hopf algebra is neither RepG or VecG. And before moving on, let me make one comment, which is that under the state operator correspondence, the states in the open string Hilbert space are of course mapped to the boundary changing local operators. So this boundary tube algebra is equivalently can be thought of as the symmetry algebra acting on the boundary changing local operators. And these boundary changing local operators will organize themselves into the representations of this boundary tube algebra. Now, to make further progress, it's going to be important to understand sort of quote-unquote topological holography or symmetry TFT for this conformal boundary conditions. And just, I'm not going to say too much about it, but just to set the notation, let me say a few words. So, of course, the relation between 1 plus on the WGW models and 2 plus on the Chern-Simons TQFTs has a long history. But recently we've been realizing that by first starting from any, say, 1 plus on the QFTQ with some fusion category symmetry, you can uplift this QFT to a boundary condition, Q tilde, over 2 plus on the dry-zero TQFT. So my notation will be that Q tilde denotes the physical boundary, and this T denotes the Dirichlet boundary condition, or the symmetry boundary condition. And then the sim TFT is denoted as a 2T dry-zero of C, whereas this C is the fusion category. And all the symmetry operators live on the symmetry, this Dirichlet boundary side. Now, sort of similar to usual holography, I think it's sort of interesting to try to fill in this quote-unquote holographic dictionary, meaning that given some physical object on the 1 plus on this side, you can ask what does it correspond to in the 2 plus on the picture. So in particular for us, we are going to ask what is quote-unquote bulk dual of the conformal boundary conditions over 1 plus on the conformal field theory Q. Now, suppose Q has a fusion category symmetry C and a multiplet of conformal boundary conditions Bi transforming into each other under the action of C. And I'll not show the details, but mathematically you can show that this collection of boundary conditions Bi, they form a what's known as module category M over the fusion category C. So the definition of a module category is not important, but we are going to use the following fact, which is that every topological boundary condition of the dry-zero TQFT based on this fusion category C, they are in one-to-one correspondence with module categories M over C. So what's the proposal? Consider you have a 1 plus on the QFT Q, defined on a, say, Lowell half plane, where on the real line I'm imposing some conformal boundary condition B. So this conformal boundary condition B will be part of some module category M over C. And the proposal is that on the 2 plus on the TQFT side, this picture on the left-hand side inflates into a picture like so, where this conformal boundary condition B sort of becomes this two-dimensional surface on the top, where on this top surface you have this topological boundary condition for I0 theory, which is labeled by the same module category M, to which this conformal boundary condition B belongs. Now, we want to understand the states in the open string Hilbert space, or in other words, we want to understand the boundary changing local operators. So now consider you have the boundary condition changing local operator O from boundary B1 to B2. Now, we propose that under this correspondence, on the 2 plus 1 this side, this operator O sort of becomes a triple where this O underline and O tilde will not play so much role, so it's not going to be too important. But importantly, you are going to get some topological line interface alpha on this top boundary. So this alpha is some line interface between two module category boundaries, M1 and M2. Now, we claim that this alpha, this topological interface, labels representations of this boundary 2 algebra. Intuitively, you can understand this as follows. So the action of this symmetry operator, D, on the 2 plus 1 this side, it becomes this symmetry operator lives on the Dirichlet boundary side. And the action is by shrinking this operator. Now, when you shrink this operator, this can potentially change this junction O underline, but it will never change the line interface alpha just because of locality. So we claim that this open string Hilbert space, H sub B1 and B2, it decomposes into direct sum of these representations, where alpha runs over all possible representations of the boundary 2 algebra. In other words, it runs over all possible topological line interfaces living on this top boundary. Okay, so where we are, we have understood that the global symmetry of the entanglement Hamiltonian is given by this boundary 2 algebra. We gain some intuitive understanding of what are the irreducible representations. These are the boundary line interfaces, alpha, which lives in the some topological boundary condition of this I0 TQFT. And as an immediate application, we can now compute the non-invertible symmetry resolved entanglement entropy, which I'm going to define right now. So since the entanglement Hamiltonian commutes with this boundary 2 algebra, we can use that to block diagonalize your reduced dense matrix rho sub A into different representation sectors alpha. Now, the symmetry resolved entanglement entropy is simply defined up to some normalization to be the von Neumann entropy of each blocks. And let me show you the results, skipping all the derivation. So if we compute the symmetry resolved entanglement entropy for some fixed representation alpha, and this is what you get. So up to leading order, the leading order is the same as the ordinary entanglement entropy. So you get this logarithmic divergence determined by central charge. And you still get the G functions for the conformal boundary conditions. But at the same order as these G functions, you get this additional contribution, which depends on the representation alpha. So now, all the details are not important, but roughly speaking, this D sub alpha, for instance, is the quantum dimension of this line interface. it doesn't necessarily agree with the actual dimension of the representation alpha, but they're related. This dB1 and dB2 so are quantum dimensions of these interfaces, B1 underline, B2 underline, and this n is some fusion coefficient between these three topological interfaces, alpha, B1, B2. So let me just give you some intuition. You can think of this fusion coefficient roughly as the dimension of the representation. It's not completely precise, but you can think of it that way. And the other part, this ratio, d alpha divided by dB1, dB2, this basically tries to measure how frequently a given representation alpha appears in your entanglement spectrum. And you can also try to remove the dependence of this regulator, epsilon, the size of the disk, by taking the difference between this symmetry resolved entanglement entropy and the ordinary entanglement entropy. And you can isolate this new contribution that depends on the representation. And let me make some remarks about this formula. So when we consider a ordinary symmetry, ordinary finite group symmetry given by some group G, and if I impose a G symmetric boundary condition at the entangling surface, then this result reduces to the following, where in this case the alpha, the quantum dimension of this line interface alpha, happens to agree with the actual dimension of the representation alpha. So alpha just labels the group representations. And this formula, rho d alpha square over order of G, was derived by many other people using many different methods, and our result reproduces this known result in this special case. And on the other hand, if we do a fusion category symmetry, some non-invertible symmetry, and if we impose a symmetric boundary condition, then this reduces to the following expression. Well, the order of G in the invertible case is basically replaced by the total quantum dimension of the fusion category. And similar formula also appeared in many recent papers. And finally, the result for completely symmetry breaking boundaries were derived for diagonal rational CFTs by these authors. And in that case, they performed some numerical tests and then found agreement. And let me just make a few final remarks. So if I impose a symmetric boundary condition at the entanglement cut, then, so as I said just in the previous slide, the formula that you get is the following. So here you get d alpha squared, roughly because one factor of d alpha corresponds to the dimension of the representation, and the other factor of d alpha sort of tells you how frequently the representation appears. But we are focusing on unitary series, and for the unitary case, this d alpha is always greater than 0, which means that if you impose a symmetry preserving boundary condition, then every possible representation of this boundary tube algebra appears in the entanglement spectrum. So there is some kind of notion of completeness of the entanglement spectrum. I don't have anything concrete to say, but it would be nice to understand the meaning of this maybe in some holographic CFTs. And another comment is that if you consider a trivial representation, alpha equals identity, we find that this formula reduces to the topological entanglement entropy of the 3D symmetric TFT. This, we also do not know whether there is a deeper reason to this thing, but it will be nice to understand it in the future. Okay, let me summarize. Okay, so we saw that in 2D CFTs, the entanglement structure of the ground state of a single interval can be analyzed using techniques from boundary conformal field theory. So the entanglement Hamiltonian has a global symmetry given by this boundary tube algebra. So we computed the corresponding symmetry resolved entanglement entropy, and the result reproduces several known results in special cases and generalizes them. And I didn't show any details, but underlying this computation, the correspondence to 2 plus 1D symmetry TQFT was very crucial. And with that, let me end. Thank you so much.
Since I have the mic, let me ask a question first.
Sure.
So one central idea in your talk is the connection between entanglement entropy and boundary condition.
Yes, yes.
Now, when we incorporate symmetries into the discussion of mixed state density matrix,
yes.
and also when we incorporate the idea of symmetry into the discussion of boundary condition, on either side there are two notions of something to be symmetric.
Yes,
right?
Yes.
Are they the same or are they not? Because during your talk, I noticed that you talk about the density matrix commutes with the symmetry. That's the weak symmetry, right?
Yes.
And I can imagine in defining the symmetry result of entanglement entropy, you also only need a weak symmetric condition.
Yeah, that's a good question. So yeah, I don't precisely know if there is any relation, but yeah, I'm not sure. Yeah.
Thanks. I have a question about, you mentioned sort of holography in passing, but do you think this could be applied for holographic conformal field theories also?
Yeah.
Like where you actually have, this is more like in the context of things like rational conformal field theories, right?
Oh no, so our derivation applies for any CFT. We don't have to assume it's rational.
But you have a finite number of simple objects in your fusion category.
Yeah, but that's our choice, yes.
Sorry? That's
our choice. Yeah.
So you could also extend it to something like Virasoro TQFT in the bulk, or?
So not immediately, but perhaps it's possible. Yeah, but our setup is that we can have arbitrary CFT, doesn't have to be rational, but the symmetry that we focus on is a finite fusion category.
Yeah, so I wondered whether you could extend it to things which don't have finitely many simples.
Yeah, that's an interesting. Of course, yeah, one special case of that will be just ordinary continuous symmetry, some Lie group symmetry that people, of course, studied.
Yeah,
but say something like Virasoro TQFT, it's an interesting question, I think, but we haven't tried.
Can I have a follow-up? Just another extension question is, when you go to 2 plus 1D,
yes.
I think a lot of the structure of these module categories just carries over.
Right.
So have you looked at whether there's an analog story here, and there the dimension of C isn't so well defined, so what would replace that?
Right, yeah, that's a good question. But yeah, we haven't tried higher dimensions, but I forgot to cite it, but a few weeks ago there was a paper, I can show you the reference later, but so my understanding is that this row of conformal boundary condition at the entangling surface, it's maybe not completely not understood in higher D, but it's sort of less understood, I think, compared to the 1 plus 1D case. Unless I understand the 1 plus 1D case better. But because in our discussions, it's sort of crucial that we know like what kind of boundary conditions that we can impose at the entangling surface. So, but it's probably possible, but in higher D, but we haven't tried.
Yeah, this might connect to the first question asked by Sakura. So is it possible, or is there any potential connection of this computation to the conventional holographic ADS-CFT? Like there are some ways you can use the replica trick to do the geometric data computation, right?
Yes, I don't really know. So, but one could ask, I don't have anything concrete to say, but it would be interesting if we can derive same formula, say, by tracing Takayanagi surface with some monoderivative defect or something like that. But it's an interesting question, I think. Yeah.
So in the beginning, you talked about this paper of Saller about the fact that you realize some specific boundary conditions for lattice systems. So how do I have to interpret this now with the rest of your talk? How do I have to, what boundary conditions are these?
You mean this paper?
Yes.
So maybe let me first, the two are related, but so the setup is that you start from some lattice model with some tensor product Hilbert space. But it's at the critical point, so it flows to some continuum conformal field theory. And on the lattice, it's straightforward how to trace out the outside of a finite interval because you just have a tensor product Hilbert space, right? So you do this and then compute the entanglement spectrum numerically, for instance. Then you can compare that entanglement spectrum with the spectrum of the boundary condition changing local operators in the corresponding conformal field theory, continuum conformal field theory. And then these two set of papers, they found a good agreement. I can give you an example. For instance, if you start from the transport field Ising model at the critical point, then the entanglement spectrum agrees very well with the BCFT spectrum. So we have Ising CFT on an interval. And then the two boundary conditions are the G2 symmetry preserving boundary conditions. And you can also do it in the, say, XXG chain. You get some compact boson in the continuum limit. And the entanglement spectrum agrees with the BCFT spectrum with, say, Neumann boundary condition imposed at the end. Both whether it's Neumann or Dirichlet depends on your T-duality frame, but anyways, you get the larger G function boundary condition, basically.
I have two questions. One is related to the previous question. So, yeah, you mentioned the fact that this boundary condition that match with the numerics that give rise the entanglement spectrum has larger G.
Right.
That's contrary to intuition because they will be destabilized by deformations. Presumably, what happens here is that there's actual symmetry. Like there's a Z2 symmetry. If you impose Z2 symmetry on the boundary, the free boundary condition of the IC model is actually the one with the lowest G, as opposed to the largest G.
Exactly. So actually, that was the point of this more recent paper. So this was just a few weeks ago. So it's a natural. It's natural to suspect that it must be a symmetric preserving boundary with the lowest G function.
Yeah.
But so in this more recent paper, they consider this RSOS models, which flow to unitary minimal models, and this, so they found that this is not true. But I don't think they included non-invertible symmetries. So if you look at only ordinary symmetry, then this expectation is not true. Okay. But maybe there is some more symmetry that's responsible for this. We don't know.
Okay. And my other question is for this symmetry resolved entanglement entropy, are there known monotonicity properties?
That's a great question, but
or possible lower bounds.
It's a great question. Not as far as I know, not quite, because these quantities are basically sort of robust, I guess. So these are some quantum dimensions and fusion coefficients of some fusion category, Modular category. So I guess, if anything, maybe they are RG invariant, but we are not sure. Mm-hmm.
Yeah, thank you. So you mentioned the example of doubled Ising CFT,
yes.
And you constructed some symmetric boundary state
yes,
under Z2 cross Z2 plus this Kramers-Wanier.
Yes.
So my question, so that is kind of new conformal invariant boundary state, or is it one of the known?
Yeah, so this is not a new conformal boundary condition, but I can tell you how we found it. It's very easy to understand. So you first start from single Ising CFT and put the Kramers duality line in the middle, and then you fold along this line. And this will define some boundary condition in the double Ising CFT, and that's this B. And you can show that this B preserves this these symmetries.
I think this boundary is in your paper with Affleck. Right?
Oh, okay, so that's my question. That's some special case. But it was not obvious. Thank you.
Thank you.
Maybe a follow-up question. So is that possible to construct the rep D8 corresponding boundary condition?
Yeah, that's a good question. I don't really know. We haven't tried, but maybe we don't know. But maybe we can use this fact that the Ising times Ising has this Z2 swap symmetry, swapping the two Ising factors, and rep D8 is basically you have same Z2 times Z2, but you multiply this N operator with the G2 swap symmetry, then you will get rep D8. Maybe using this fact and similar tricks, maybe it's possible to find rep D8 symmetric boundaries, but I haven't thought about it too much.
You were mentioning that the unitarity implied that dA or dA squared was greater than 0. So right. How much of this carries over to non-unitary CFTs?
So for non-unitary CFTs, so a lot of things will change. For instance, if you have a non-unitary CFT, even the leading term will change. So I can even, I don't even have to talk about symmetry with reserved versions. But so the thing is that in the non-unitary case, this central charge C, for instance, will be changed to something known as effective central charge. So basically, the leading term comes from the identity operator contribution from the closed string channel. But in the non-unitary case, the identity might not be the true ground state, and then you need to have the true ground state scaling dimension here. And so that will change. And sub-leading term, I don't know, but yeah. Because already the leading term changes here. It's a significant change, I would say.
Thank you.
Okay, well, if there's no more question, let's thank Yichul and Mike for two very nice talks.